Hi everyone. This video we're going to talk about total hardness. So there will be three parts. The first part we will discuss the theory of total hardness. The second part we will look at the titration, which is used to measure the total hardness in a water sample. And the third part of the video we will look at the calculation for that titration. So to start off with, this is taken from your book on page 460. Total hardness. Water is said to be hard when it is difficult for it to form a lather with soap. Hardness is caused by dissolved calcium and magnesium salts, in effect by calcium and magnesium ions. Now I'm just going to go to the next page, page 461. The total hardness of a water sample is estimated by titrating the sample with a standard solution of ethylene diamine tetraacetic acid. It's shortened to EDTA. You don't need to know what EDTA stands for. Now, total hardness. So total hardness is the combination of temporary and permanent hardness together. So this experiment or this theory is discussing all the hardness in a water sample, as in temporary and permanent. So as we mentioned, the reagent used is EDTA. This reagent forms stable complexes with calcium and magnesium ions. Basically, this reagent reacts with calcium and magnesium ions when the pH is above 9. The pH level is achieved by adding a buffer solution. Now, a buffer solution is a solution that keeps a reaction or a solution at a certain pH. So basically, you pick the buffer to suit the reaction that you're doing. In this case, a pH buffer of 10 is chosen. That's useful here because we need to keep the pH above 9. In order for the reaction to occur. The EDTA reagent can be used to measure the total quantity of dissolved calcium and magnesium ions in the water sample. In other words, total hardness. Since EDTA cannot distinguish between calcium and magnesium ions, the total hardness is conveniently expressed as parts per million of calcium carbonate, CaCO3. So what this means is that EDTA doesn't react with only calcium ions or magnesium ions. It reacts with both. So if there are calcium and magnesium ions in the water sample, the EDTA will react with both. It doesn't distinguish. It will react with both of them. Now, this is an important point to note. The concentration is expressed in parts per million, that's fine, but of calcium carbonate. Now, some of the hardness in the water may be due to magnesium ions or calcium ions. So it would be incorrect to write down parts per million calcium or parts per million magnesium. So what scientists have done is they've come to an agreement or a convention. A convention is an agreement between a group of people. In this case, scientists. They have agreed to express the answer in parts per million of calcium carbonate. Even though calcium carbonate is insoluble in water and it does not directly cause hardness itself. It can't cause hardness directly itself because it doesn't dissolve in water. However, scientists have agreed, just for simplicity, to express your answer in parts per million of calcium carbonate. Now, EDTA itself is not a primary standard. However, the disodium salt of EDTA is a primary standard, and it's more soluble in water than EDTA itself, and is consequently more commonly used as the reagent than EDTA. Now, if you look up here, this is the structure of EDTA. For those of you that like to be able to use a name to figure out a structure, basically ethylene, even though there's a single bond here and not a double. That's your ethylene part. Amines, the carbons with nitrogens attached. They're amines, diamine. So two of them. There's one, there's another. Tetraacetic. So tetra meaning four acetic acids. There's one. So acetic is the old name for ethanoic. Ethanoic meaning ethanoic, two carbons. And there's your ethanoic acid, 1, 2, 3, 4. So that's your EDTA structure. So disodium EDTA would have two sodiums attached. Now, you don't need to make sense of this. Basically, this is just a shorthand way of representing this structure with two sodiums. Okay, that represents the salt. It ionizes in aqueous solution to give that, so the sodiums are released into solution. And that which complexes in a 1-to-1 ratio with either calcium or magnesium ions, which are represented as M2+. M for metal. In this case, the metals of interest are calcium and magnesium. The equation for the reaction is the disodium salt. One of them reacts with one of these ions to give this. So that's your metal complex, and hydrogen ions are released. The most important thing from this, you would be given this in the exam if you're asked about total hardness. The most important thing here is one of these reacts with one of these. It's referred to here, look, a 1-to-1 ratio. So 1 mole of these reacts with 1 mole of those. Solutions of EDTA should be stored in plastic containers rather than glass bottles. And not just EDTA, but also the disodium salt, which is used. The reason for this is if the solution is stored in glass bottles, its concentration will decrease appreciably with time as metal ions are extracted out of the glass. So there are metal ions in glass and they go into solution. And as we see here, metal ions react with EDTA. If they react with EDTA, well then the concentration of the EDTA will be decreasing. So over time, the concentration of EDTA would decrease if it's stored in a glass bottle. And for that reason, they're stored in plastic containers instead. Now, in the titration, the indicator used would be areochrome black tea. This indicator is dark blue in color, but changes to wine red when complexed with calcium or magnesium ions. Thus, when the indicator is added to the water sample, a wine red color appears if these ions are present. So the end point would be then, obviously, it starts off as wine red, and when the titration is over, you get a dark blue color. However, EDTA forms a more stable complex with the metal ions, so as the titration proceeds, the metal ions break away from the indicator and complex with the EDTA. When this occurs to a sufficient extent, the blue color of the indicator is restored. So that's all the theory to go with total hardness. The next thing I'm going to discuss now, part 2, is the experiment. So the experiment is on page 462. Estimation of total hardness of a water sample using EDTA. So I'm just going to go through the procedure like I would have done in class. Step 1, copy the table into your report book. Table is on the next page. Okay. Now, most of this is a straightforward titration. There's nothing really different. There's a couple of points which I will highlight when I come to them. So step 2, you prepare your burette by rinsing with deionized water, and then you rinse with the solution that you're going to use. The solution that you're going to use is the hard water sample. I'll correct myself there. The pipette is rinsed with the hard water sample, and the conical flask is rinsed with deionized water. This is very important that deionized water is used here, because ordinary tap water would contain calcium and magnesium ions, so that would affect your result. Fill the burette to the mark with EDTA solution and make sure that the part below the tap is filled. Now, the solution that goes into the conical flask, there are very few cases where you don't use 25 mils. As you remember, all the pipettes that we have are 25 ml pipettes, and normally you just transfer 25 mils into the conical flask for all titrations. Here is one example of where you use 50 mils rather than 25. This would be, you don't have to remember that, but just if it comes up in the exam, just be careful that when you're writing down the volume for what's in the conical flask, that it's 50. That would be said in the question, but just out of habit, you might put in 25 as opposed to 50 when you're doing the calculation. So pipette 50 mils of the hard water sample into the conical flask. Add 2 to 3 mils of the buffer solution. That's important to keep the titration, to keep the solution in the conical flask at above 9, pH 9. Using a spatula, add the solid indicator to the flask in minimal quantities with swirling until a deep wine red color is obtained. Carry out one rough titration and a number of accurate titrations until 2 titers agree to within 0.1 of a mil. The end point is reached when the color just changes from wine red to dark blue. And then use the data to calculate the total hardness of the water sample. Okay, so important things to point out there. Just in the pipette, you're going to transfer 50 mils of your sample. Also, you should use deionized water, because tap water would contain metal ions that would affect your experiment. And then just to remember the color change. Starts at deep wine red and finishes at dark blue. Now, part 3 of this video will be to talk about the calculation involved in this titration. Now, I'll be attaching this sheet on Classroom. So this sheet will be available for you on Classroom. You can pause it and take a screenshot if you want, or it will be in a post on Classroom. Okay, so imagine now that we've carried out the experiment, the titration, and you have your results. Now I'm going to use results from an example. It's on page 462 in your book, and it's example 21.3. So these are the results that were given. So 50 mils of the hard water sample were used, and they required 28.35 mils of your EDTA solution. Your task is to calculate the total hardness in parts per million of calcium carbonate. This is the reaction. If this came up in the exam, you would be given the reaction. Okay, as I said before, this just represents your EDTA ion, or your disodium EDTA ion, and these are the metal ions that it reacts with, calcium and magnesium. Note that it's one of these reacts with one of these. So I'm going to use the left-hand side underneath the EDTA for the M1V1N1, and I'm going to use the metal ions, calcium, magnesium, that cause hardness, down the right-hand side. So we just fill in as normal, your M1V1N1. So for EDTA, they give the concentration. That's your burette reading, and one of them reacts with one of them. We're interested in finding out the molarity of the calcium and magnesium ions. And remember, we use 50 mils and not 25. Fill all this into the formula that we were used to using. When you fill it all in, it gives you concentration for M2 as 0.00567 moles per liter. Okay, now it has asked us to convert that into parts per million. So here's how you do it. Okay, so let's follow it over here. Currently it's in moles per liter. We need to change that into grams per liter of calcium carbonate. The first thing we need to know is, well, 1 mole of calcium carbonate is 100 grams. As normal, CaCO3, 1 mole is 100 grams. So we need to multiply this answer by 100 to change this from moles per liter into grams per liter. When we do that, we get 0.567 grams per liter of calcium carbonate. Now, ppms, that's milligrams per liter. So we need to change this grams into milligrams. We do that because by multiplying by 1,000, because there are 1,000 milligrams in a gram. So when you multiply by 1,000, you get 567 milligrams per liter. This is the equivalent of ppms. So 567 milligrams per liter is the same as 567 ppms. And that's it.